Get started. It's awesome. So thank you so much for coming today, everyone. So I'm going to be talking to you about some surprises from puzzle video games. So I'm going to kind of do, there's going to be four different things I'm going to talk about today. As a warning, the first two are a little bit technical, but I'm going to try to go through those really, really fast so then I can talk about some more of the fun stuff afterwards. Um, so the first thing is cellular automata, which are some of the really fun things to play around with. So these are basically came from Stephen Wolfram, and he tried to classify these cellular automata, which basically you would have would update a one-dimensional grid of cells, which were either binary on or off, and he would update them according to a very simple set of rules. So we have a very simple set of rules here, such as if there are three consecutive black cells, then we replace it with a white cell below it, or two black cells in a white square, we replace it with a white square below it, and so forth. And so this is just a very particular rule. It's rule 28, which has to do with the binary encoding of it. But what's very interesting to see is we have this very simple rule, and we can start with a very simple initial condition, which is one single black cell, and see how it evolves. And it creates this kind of pattern, as we see below. And this pattern isn't anything super interesting, but we can dive into it a little bit to see if there's some underlying structure that's going on here. And one really interesting thing that we can do here is if you consider each individual row of the diagram above, if you consider the black cells as being 1, the white squares as being 0, you can try to convert it then into a binary number. So for instance, the very top row is just a single black cell, so that's 1. The next one is 1, 1, which would be converted then to the decimal number 3. The next cell, there's a black square, then a white square, then a black square, so it's 1, 0, 1. So that'll be the binary decimal number 5, and so forth. So in this way, we started with a cellular automata pattern, and we got a sequence of numbers out of it. And it turns out that the sequence of numbers actually has a very simple characteristic. And it just follows from a very simple recursive formula, which is given by this expression right here. So the sequence of numbers was like 1, 3, 5, 11, and so forth. And it satisfies this very simple recursive rule. And you can play around with it. You can do some generating function stuff to actually fully characterize this entire sequence of numbers from this entire pattern into a single concise expression. I'm not going to go over the details of the math, it's irrelevant here. But the very interesting thing to notice here is its overall pattern of what we just did. So what we started with was we started with a cellular automata rule. So we started with a very specific rule, rule 28. We saw that this produced an interesting binary sequence of behavior, which then in turn led to a generating function, which was able to generate that entire sequence of data. And that's an interesting schema. However, I would say that none of this behavior is very surprising. What we started with was a very simple rule. It produced a somewhat predictable pattern, which can then be summarized with a somewhat simple recursive formula or a simple algebraic function. Now, what I'm really excited about and what I'm really interested in is can we make some small changes to the setup? So everything above here was pretty predictable. Can we make some small changes to the setup to produce behavior that actually is surprising now? And that's going to be the key theme of my talk today. And I'm going to show how making very small changes in systems can lead to really surprising and interesting behavior. So going back with the cellular automata example, so there's in total 256 basic cellular automata. And those have to come from, if we remember from the basic slide here, there's only 8 possible patterns, so just 2 to the 8th power is the total number of cellular automata that exist. So Stephen Wolfram, who thought a lot about these, he classified these 256 basic cellular automata rules into 4 groups. And we can kind of see these classifications here. So class 1 is a cellular automata that converges to a uniform state very quickly. So they kind of start off with something interesting going on, and then it quickly converges into like a single color, basically. Class 2 is going to converge to a repetitive or stable state very quickly. And that was what we just saw with Rule 28. It was a somewhat stable state. There wasn't anything too unpredictable going on. It'd be fairly easy to make predictions based upon what would come next. But what's really interesting, and this is what when I'm saying the word surprising, this is what I'm kind of more getting at, is these class 3 and class 4. Because class 3, which we see in this picture here, it's a random state, which has no apparent pattern going on. And what's really interesting too is class 4 is there's actually a sequence of cellular automata that are capable of universal computation. So they're Turing complete in that sense. Yeah. Hmm. What do you mean? Yeah, no, that's a good point. Maybe I guess rather the place of all these triangles are what would be unpredictable. There are patterns though within it still. So no, that is a good point. We can still try to find patterns, but just where all the triangles are spread out through this grid seems to be somewhat random. You would agree? Yeah. So, what's very interesting here to me is so that to try to produce, to go from this class 2 behavior, where it's very predictable behavior, to somewhat more random or stochastic behavior, you might say that you have to make a really big change in order to do this. And I claim that it's actually somewhat simple to do this. And in fact, we only need to change a single bit of one of the rules to go from a class 2 system to a class 3 system. So rule 28 was given by this rule set here. And rule 30, which actually just produced that triangle grid that we were talking about, is almost exactly the same, except the only difference you notice is if you see a white square, and a black cell, and a black square, then we replace it with a white square in rule 28, and then in the other hand, in rule 30, we replace it with a black square. So we literally just switched a single bit. And now, whereas rule 28, what we saw before, produced very predictable behavior, now, Rule 30 produces this more random behavior. And if we extend it out even for more time steps to 100 time steps, you see you get something that looks like this. And yeah, what James said was exactly right, that there is some underlying patterns going on here. Overall, though, this is, for the most part, total randomness. And actually, Stephen Wolfram has offered like a $20,000 prize or something if someone can find some underlying structure in Rule 30. So it's just a fun project if anyone wants something like that to work on. But so, anyways, the key takeaway here is a very small change in the initial system led to a very drastic change in the outcome of the system. Let's talk about one other instance where some very small changes in the dynamics can lead to really drastic outcomes, and then I'm going to kind of talk about the puzzle games that really excite me. So we'll talk about a logistic mapping really quickly, which is just basically something that's used for population growth and for some other applications. It just follows a pretty simple algebraic expression for an update, where you just take xn plus 1 is a constant r times the previous value times 1 minus the previous value. And you can basically try to see what x value it's going to converge to. And you take an x value maybe between 0 and 1 and try to see where it converges to. And we can see what happens if we apply this rule for 15 or 20 time steps. And when I apply for 15 time steps, it starts off pretty predictable. There's nothing really too shocking going on. All of a sudden, something really weird happens around this 3.5 point. And same thing when we apply it for 20 time steps as well. And the other kind of interesting thing too is at some point it seems like the graph's kind of split because when I apply it for 15 time steps, it kind of goes downwards here, whereas if I apply it for 20 time steps, it goes upwards. So what's going on here? This is really strange behavior. It's a very simple quadratic expression. What's all this weirdness going on? And so if you were to actually fully extend this out, we'd actually get a bifurcation diagram. And what's going on here is depending on the number of time steps that you extend it to, the convergent value that it goes to can actually split into two possible different directions, which we kind of saw in this graph here, where one went downwards and one went upwards. So for any value of r between 0 and 3, the update rule all converges to the same value, which is r minus 1 divided by r. Now, at r equals 3 here, we see that we have our first split, and that was just depending on whether n is even or odd. In one diagram, I showed it for 15 steps. The other one, I showed it for 20 steps. Now, at around r is 3.5, a little bit less than 3.5, there's a second split of values that we see happen here. And then at a little bit past 3.5, 3.54 or so, there's a third split that we see in this diagram. And then at about r is equal to 3.56 or so, It's just total chaos in the diagram. And there's no really any more apparent patterns. It seems to be just total randomness that's going on. So, what's going on here? But what's really interesting is we can take this total sequence of randomness where it looks like there's a bunch of stuff going on, and we can still find some order underneath. So if we consider the sequence of points for which this graph splits at, we let this be a sequence B sub I. If we consider the successive ratios of the differences between the points that the graph splits at, this actually approaches a known constant. So we took that first splitting point, which is around 3. We take that second splitting point, which is about 3.4, and then so forth. And we look at what the ratio tries to converge to, and it actually begins to converge to a constant. And the value of this constant isn't super important, but it's shown there. And now this might not seem super surprising. So it says, okay, this is a weird sequence. We had some randomness, but we found some known order within it. But actually, this constant shows up in so many unexpected places. So if you take the Mandelbrot set as well, the Mandelbrot set, which is basically just, again, applying a simple quadratic function and then trying to see which points extend off to infinity and which points will stay bounded within a certain region. And this produces a really chaotic system. But actually, if you take a look at, it's basically the ratio between successive diameters in this graph, it actually has the same exact structure as the previous graph. And there's a really beautiful visualization online, a YouTube video that actually goes through and shows this. And you can see that as you go along the Mandelbrot set here, that it will have the same exact structure with this Feigenbaum constant. So I think this is really neat that this random constant shows up in two totally seemingly disconnected places. So just to summarize some of the things here, we saw that simple rules can lead to dynamic and beautiful emergent behavior. We saw how in the cellular automata case, a very small change to the dynamics of the rules can lead to a drastic change in the behavior of the system. Similarly, with the logistic mapping, a small change in the value of R can create chaos with the various bifurcation points that we had. And now I'm going to talk about the stuff that I find super cool too, is I'm going to see applications of these ideas leading to surprising puzzles in two of my favorite video games, The Witness and Baba Is You. Are there any questions or comments up until this point? Yeah, so it's basically this thing that if you iterate any, I think it's any mapping, and ultimately that will have some type of splitting at some point. It basically, and you take these ratio of these two, the points at which it splits at. So when you take the difference between like this 3.544 point and this 3.44 point and divide it by the previous ratio, it's basically the limit as all of these ratios will approach. Yeah, yeah, but it's two totally different systems that basically both have the same underlying structure, and that's kind of the cool point that we have. Yeah, you're welcome. Cool. So let's talk about Baba Is You. So Baba Is You is a Sokoban style game. So players push boxes on a screen. Rules are on the screen as sentences, and the players can move along the four cardinal directions to interact with the rules, basically. So here's one of the simplest and first puzzles that people will approach in the game. And what I actually want to do to illustrate some of this is I'm just going to have the game booted up in a separate tab. Let's see if I can share that. And we'll see how the interesting things that can come from this. Give me 1 second here. Okay, can people see that? Awesome. Okay, so this is the very first level of the game. And you'll see that there's some very simple rules going on here. So first off, you just move in the four cardinal directions, up, down, left, and right. We have this first rule, which just says Baba is you, which basically means that this sheep guy that I'm controlling is me. Um, We have some other rules as well, such as wall is stop, which kind of works as expected. If I try to move into a wall, I'm unable to now. We have rock is push, which means that these rock objects are things that I can push and move around. And then finally, we have flag is win, which basically says that when Baba overlaps with the flag, I win and beat the level. Okay, that wasn't particularly interesting. So let's look at some of the things that we can actually do to mess with this and change things around. So let's take the wall of stop, for instance. I break up that sentence so wall doesn't stop anymore, and all of a sudden, I can move through the walls. Let's see what else I can do. Let's take the rock up there. So if I move rock all the way up here, all of a sudden rock is me. So now I'm controlling this set of rocks. If I break this, however, at any point, then all of a sudden nothing is me and the game would just end. So I would have to undo that. Um, what else could I do? I can maybe make instead of flag is win, let's make wall is win. And then all of a sudden you basically win the game just by overlapping with the wall. So you can see, even with very simple set of four rules, you already create some interestingness with the puzzles going on. So I'm going to go back to the slides really quickly here. So I want to talk about how puzzles from this game basically come from surprising interactions. Give me a second to... All right, so back to the slides now. So one thing that's interesting is that the game never explicitly teaches the players the rules of the game. It instead has these tutorial puzzles that introduce each of the new mechanics. And the game creator basically said, if I exhaustively go through all the meaningful interactions between all these different elements, eventually I get levels where the trick is mostly just the basic functionality of a specific element in itself. So that's how he creates these basic tutorial puzzles within the game. But then you want to extend upon that because just tutorial puzzles don't make for a very interesting puzzle game. So in general, what the game developer does is he begins by thinking about all the interesting interactions between the rules of the game then. Because there's many different words that have different meanings, and he tries to think, how can I take advantage of these different interactions to make some interesting puzzles? He then uses reverse engineering to come up with a puzzle that basically forces the user to come up with this clever idea themselves. And he does this by restricting the player on what they can and can't do within the levels. And these restrictions basically means that the player can only spend so much time exploring ideas that don't work before they find ideas that do work. And to demonstrate this, I'm actually going to go back to the game really quick and show one of my absolute favorite puzzles. I'm trying to keep this as spoiler-free as possible in case anyone decides to pick this up at some point. Okay. Excellent. All right, so we're back in the game now, and this puzzle is basically a tutorial puzzle that I'm showing right now, and this introduces the word not. And as computer scientists, hopefully we all have a pretty good understanding of what the word not means. So let's try to see how a puzzle can use this. So we have this fence area, and fence is stopped, so we're unable to get out of this fence area. We can do something interesting right off the bat. So I see I have the not word, and I can try making not Baba is you. And now all of a sudden, every single one of these things that was not Baba becomes me. Notice that fence doesn't become me though, because it says that fence is not you at the top left. So all of a sudden, I'm controlling all of these other elements of the puzzle. But that's not going to help me break out of this cage and actually get to the win condition. So maybe instead of doing that, I'll make Baba is me again. So maybe something instead I can do is I can make the sentence, oops, I did not want to do that. I can make the sentence, fence is not stop. And notice that right now it says fence is stop, so that actually overrides the previous sentence that said that fence is stop. So now I have fence is not stop. And now I have the is and when condition, And I can very simply go up, and at the same time I made Baba is you and Baba is Win. So I beat the puzzle. But now, what's very interesting is so, okay, that was a fairly simple puzzle. All I had to do to beat it was basically make fence not stop. Now, this next one here extends upon the idea, but it just made one really small change. And all that it did was it removed the word is. So previously I had the is win down here, and now I just don't have the word is. And I claim that this makes for a much, much more interesting puzzle. Because I'm going to start the same exact way. I'm going to make fence is not stop. And now I have this win word, and I need something to be win. But I don't know what I can do, what I can make to be win. So one thing that I could try is maybe I can make fence win. And you notice that the fence gets all shiny now? However, I can't beat the puzzle because fence is stuck. So I'm not able to actually interact and overlap with the win condition. Um, I could possibly try making fences you. However, it says fences not you, so I'm not able to do that as well. I'll give this as an opportunity for if anyone here has an idea. There's one very simple four-word sentence that I could do to instantly beat the level. Can anyone think of it? So I need to make something win, and I can't make fence win. How can I maybe apply the not operator there? Let's see. If I make the sentence not fences win, then Baba would fall into the category of something that is not a fence, and then you would beat the puzzle basically. So it's a very simple trick. It almost kind of seems like one of those world tricks where it's like you kind of have to just like invert the logic on itself, but it just made a very small change to the puzzle, and then all of a sudden we got a drastically more interesting puzzle out of it. All right, let's switch back to my slides over here. All right, so I'm back to my slides. And we saw that the difference between these two puzzles, where they were the exact same puzzle, literally the only difference between them was just this one word is. And removing that one word is constrained the player even further so that they had to come up and notice this new interesting interaction. And that was very similar to what we were talking about with the cellular automata rules from before, where we made a very small change to a single bit and we got a vastly more complicated, more chaotic system because of that. All right. I'm gonna go for just 5 more minutes, but I want to really quickly talk about the witness too, because the witness employs a lot of these same ideas as well. So, the witness is a beautiful open world puzzle game where the solution to every puzzle is basically a path from a start node to a goal node. So in this case, the start node is a large circle in the bottom left here, and the goal node is the half circle in the top right. So the grid is four connected along the black edges, except for in the case of broken edges, which you can't pass through, and the path can never intersect itself as well, is a fundamental rule of the game. So in this case, for this puzzle, the solution to it is just shown here. You basically just need to find a path from the start node to the goal node that doesn't go through any of the broken edges. So seems fairly simple enough. But now we're going to talk about how puzzles are actually designed within this game and how they come from kind of surprising interactions. So what Jonathan Blow does, who's the developer of this game, he starts with a interesting mechanic. And in this case, the interesting mechanic that he's really going with is just drawing a line from a start node to a goal node. And then he tries to come up with a rule based on the observations from the mechanic and the principle. So, as an example of this, notice that in the previous puzzle, for each of the gray squares that are in the grid from before, a certain number of lines will be adjacent to that square. He then tries to think through what are the consequences of the rule and what interesting constraints can it make as well. And then finally, after he's come up with all these elements, he just comes up with a puzzle utilizing this rule, possibly in conjunction sometimes with other rules. So going back to that previous observation, so we're drawing lines, and the observation was just as we're drawing lines, the number of triangle uh, the number so the line will intersect each of the squares a certain number of times. So for instance, as the line goes up for this gray square right here, it intersects it twice. So the puzzle element is we basically put the number of triangles as the number of times that a line intersects that line. So in this case, we put two triangles in it because there's two edges adjacent to the square. For this square, there are three edges adjacent to it, so we put three triangles in it. Or for this square right here, there's only one edge adjacent to it, so we put one edge in the triangle there. Or sorry, one triangle in the square there. So that's our rule proposal. We just noticed something interesting about drawing lines, and we came up with a puzzle rule based upon that. And now the next thing that we have to think about is what are the consequences of the rule? And one interesting consequence is that if there's a square with two triangles in a corner, then there's one of two possible paths that it can go through. It can either go up and then right, or then right and then up. So, and then this rule can be applied to a somewhat complicated puzzle. So this is a more complicated puzzle. I'm now on a 4x4 grid. And if we had time, I would give people a chance to give it a go themselves, but because I'm running low on time, I'll show the solution here. So the solution to the puzzle is as follows. And you notice that basic constraint that I was talking about there, where as it goes along a corner, it either has to go up and then right, or right and then up, is enforced at every single one of the squares. And actually, when you would be solving this as a human, that would be basically the way I'd go about this. I would think about for each of the corners, what is the path that I have to go through that corner? So here's another further consequence of the triangle rule, is that if there is ever a triangle or three triangles in a single square, then there's one of four possible paths that it has to go through. And these four paths have to emerge from the no self-intersection rule, because it basically says that when a line intersects one of these three triangle squares, then it has to go through at one of these specific angles. It can't go through it twice, basically. And because of this limitation, when we have a three triangle square, it can create a very interesting puzzle. Because now all of a sudden the players are very much so constrained by this rule. So, for instance, in this puzzle right here, we see that there are three squares that actually contain three triangles in it. And this one, I'm actually not going to show the solution because I like to leave people with something that if you enjoy this type of puzzle, you can go home later and think about this a little bit more. So if you want to, you're absolutely welcome to give this puzzle a try. Message me on Slack or email me if you think you've got it. But at least I created this puzzle last night, and even after creating it, it took me probably half an hour to solve. So even with just very like seven simple elements, all of a sudden just noticing this interesting rule, we've created an interesting puzzle that is hard for humans to solve. And that's basically it. I had some follow-up links if you're curious to learn any bit more, some stuff about cellular automata, some cool videos on Baba Is You, and then the witness. And there's also a website where you can go play some witness puzzles or build some witness puzzles as well online. So thank you very much for your attention, and I'll open the floor to any questions.